All right, so far in our story of quantum mechanics, we have a fellow by the name of Max Planck. And Max Planck came up with the idea that perhaps energy is not something that you can just have as much as you want of. Energy is available only in tiny packages. Just like when you go buy sugar at the store. You can buy a 5-kilogram bag of sugar, you can buy a 2-kilogram bag of sugar, you can even buy little individual sugar packets for your coffee, but you can't just go in and get any amount of sugar that you want. Unless, of course, you go to the bulk barn, but we'll forget about the bulk barn for that analogy. And even at the bulk barn, sugar is still only available in the tiny molecule of sugar. You cannot get any less or more than that. So in a sense, sugar is quantized because it's a tiny molecule. So if you think about, this is a bad wording, but if you think about, a molecule of energy, there's a little blob of energy, and you can't get any less than that. Now, the energy that we're talking about exists in photons, because remember, Max Planck was trying to design a better light bulb, and his work was applied to the black body radiation problem, the UV catastrophe. So what we have is he decided that the energy in a photon, let's do it like this, E with a gamma is HF, and this was his great equation. Or of course it comes in the other form, the energy in a particular photon is HC over lambda. So a photon, we're beginning to use these words. A photon is basically a little packet of energy. Packet of energy. A photon is also called a particle of light. Now, the problem with quantum mechanics is people often talk about, wave-particle duality. Things can be waves and particles, and sometimes light is a particle and sometimes light is a wave. That's not really true. Light isn't what it is sometimes. It's always light, and it's always both. And so what we have to get our heads around is the idea that there is a thing that exists in the universe that is neither a full particle or a full wave, but is a little bit of both. So a photon is the word we use to describe a little package of energy contained in electromagnetic radiation. Okay, so we had that. We found out that when Max Planck's idea of quantization was applied to the UV catastrophe and the problem that was observed with how black body radiation did not match what we observed, our predictions based on classical theory, what it was supposed to be didn't match. And so then we applied Max Planck's idea of quantization, and voila, the black body radiation problem was solved. You'll recall that we talked about how the predicted value for energy as wavelength got smaller, so you get smaller going this way, was an infinite amount. But the observed graph did not look like this at all. It had like a blob or a peak in it and looked something more like this. And of course, we've talked about Wien's law, the Rayleigh-Jeans law, and this peak radiation, and we've done some work in figuring out what the peak radiation would be for some particular object that was being heated, and we used this Wien's law times 10 to the negative 3 divided by temperature. So we saw that there was a relationship between temperature, and Max Planck's idea of quantizing energy makes the math fit the observations. So that was a huge breakthrough. Okay, right around this time, another fellow was doing some work, and he's a very popular fellow. His name was Albert Einstein. And he was working with light, and he was discovering something very interesting. You might think that it's his theory of special relativity for which he is most famous, but this is not the case. This is something called the photoelectric effect. And this, in fact, is what won Albert Einstein his Nobel Prize. He got nothing for relativity except immense popularity and fame. But the photoelectric effect was something that he discovered that gave him the Nobel Prize. So what is this photoelectric effect? Well, Albert Einstein noticed something very peculiar. And it has to do with the way light shines and bounces off of metals. So you will recall back in grade 9, if you have an iron atom and you bounce off a couple of its electrons, right, let's say 2 of them, you leave the iron atom ionized, and we have an iron ion, Fe2+, because it's lost 2 electrons. Well, what's interesting is light energy, electromagnetic radiation, can actually knock electrons off of iron, or metals, any metal in particular. Some metals more than others, because every metal has a certain affinity for its electrons based on its atomic structure. So, the photoelectric effect then, very simply, is the ejection of electrons from metals by electromagnetic radiation. Essentially, you shine light on metals and electrons are released or liberated. The common word we use is liberation. And you can see that this would have been the beginnings of understanding how things like solar panels could possibly work. How is it possible that we could get electricity by shining light on metals, like in your calculator and other solar-powered things? Okay, so let's go through, generally speaking, how Albert Einstein put this together. So what he did is he built a little machine, and we'll just draw a sort of vague picture of it. It had 2 plates inside of it, two metal plates like this. And those metal plates were attached to a voltage control. So there was a voltage applied to the plates. Let's put a positive this way, like this. Whoops, oh, that's messed up. Okay, so we have a positive here and a negative here. And then this was all encased in a glass tube that looks something like this. So I'm just going to erase this up here. So it's going to get in the way. Okay, so this glass tube was something like this. Well, the wires don't really matter, but as long as the plates are in a glass tube. So it was sealed all up like this. And then what he did is he took light of various different colors and he shone the light into here and allowed the light to strike this metal plate. So that would be the photons of light of a particular wavelength, some lambda. And he found that sometimes that light would cause electrons to fall off or be liberated from this metal plate. But you'll also notice that because of the voltage across the 2 plates, there is a field produced. So if I just gently put in a couple little arrows to show the electric field that's being produced in this region, you'll remember that electrons, if they are released, here's an electron released, whoops, there he is, been ejected off of the metal. Now what does he do? He feels the electric field and he would shoot across and strike the other plate. And of course then he would flow through the wires and around, and we could get a current flowing across this gap because we were releasing electrons into the gap by the light striking the plate. Now this gap is very small in reality, but it has to be big in the picture so you can see it. So effectively the light makes the current flow around this circuit. So what he decided to do was he decided to make this, we put a little arrow across here, we call this a variable voltage. So you can turn it up and down, basically not just a simple battery, but a device that had a dial So you could change the voltage. And so if you imagine there was no voltage at all, when the light were to strike the plate, the electrons would be liberated and they'd just kind of float around there near the plate. Let's draw that one plate here. So no voltage applied. No voltage, that says voltage. Right, so here's the other plate. If you liberate an electron, the light would shine through, hit the metal, the electron would hop off, woohoo, I'm free. But because there's no field, the electron doesn't go anywhere, and very quickly it would be reabsorbed by the atom. Okay? And then it would be of no significance. However, if you start to turn the voltage up a little bit, you can get to the point where you can just begin to get electrons to be free. So what Einstein envisioned is that when these electrons were released, they would be knocked away from the atom with a particular amount of energy, and that energy would be present as kinetic energy in the moving electron. So he thought, all right, if an electron, let's erase this guy here and go back to start to his reasoning. If this strikes the plate and the electron is released, it's going to have kinetic energy, which means it's going to be moving. Now it's possible that if you put the plates close enough together, even with no voltage, just by luck, some of the electrons would have enough kinetic energy to reach the other plate and possibly make a current that could flow. So he decided to take his apparatus and reverse the current. So let's try again. I won't draw the tube. So the light strikes. He's got a voltage, this time sort of a reverse voltage. So instead of the positive on this side, he's got negative like this. Reverse the polarity. Negative, positive. This is now a negative plate, and this is a positive plate. Well, electrons, when they're released with their kinetic energy, here's the electron. He's released, right? Woo! Oh, I don't like that. Away he comes back. And he would be repelled back to the positive plate. So the voltage in the plate, across the plates, becomes sort of a push in this direction, whereas the kinetic energy of the electrons is sort of driving them in this direction. So Einstein said, well, what if I turn the voltage way down low? So there's very little of this push in this direction. Well, then the kinetic energy would win out, and some of the electrons would have enough energy to reach the other plate and make a current flow. And so if you put a little ammeter here to measure current, he would measure small currents because of the light. And he said, well, what if I make the voltage bigger, slowly, gradually? Well, if I make it really big, then it will outweigh the kinetic energy, and all of the electrons will then do the old turnaround and back because of the electric repulsion, and there would be no more current flowing through the wire. He said somewhere in between is the magic voltage that would be just enough to stop the electrons. In other words, what if the voltage could somehow balance out the kinetic energy? If I just adjust it enough so that the current completely stops, but I don't put any extra. And what he called that was the stopping potential. The stopping potential. Remember that potential is another word for voltage. So we could just call that the stopping voltage. Stopping voltage. If you were to raise the voltage just enough so that the force in this direction just matched the force in that direction, he could then equate those two, and he could determine how much kinetic energy actual electrons had at that exact moment of release. And that's pretty impressive. So here's what he gains from this. He realizes that the energy of the incoming photon, which was the blue wavy line of light, has to do two things when it strikes the apparatus. When it strikes the metal plate, it has to do two things, or provide two amounts of energy. One is the kinetic energy of the electron that's been ejected. The other, of course, is the amount of energy needed to actually just knock the electron free. And that, of course, is what he was trying to figure out. With the stopping potential just equaling enough to stop the current, he could figure out how much voltage there would be needed to just knock an electron free, but then it would have zero speed. It's getting it out of jail, releasing it from the bonds of the atom, the attraction to the nucleus. So he called that the work function, W, with a little zero beside there. And this is called the work function. And it represents basically, it's very similar to the ionization energy from chemistry. It represents the amount of energy needed to knock the electron free, but then there's no energy left over to have it have any kinetic energy. So it has zero kinetic energy. So in other words, if you have the energy in a photon of light, and that energy is equal to the work function, what you will get as a result is a free electron with no kinetic energy. A free electron with no kinetic energy. Then, if you were to have a photon of light that had more energy, a larger photon of light with more energy, then you would end up with freeing the electron and leftover kinetic energy for the electron to move. So this little relationship here is really the photoelectric effect summarized. All right. Now he didn't stop there. He realized that the energy in the light had to have enough to free the electron and give it kinetic energy. Then he decided, well, let's see what happens then if we take brighter light. He started to shine brighter light. And he expected that if you shone brighter light, that he assumed the brighter light would have more energy, and that would make more electrons free and a greater kinetic energy and a stronger current in his apparatus. Nope, that did not happen. His observations were that the current did not change with brightness. And that sounded weird. Because typically, brightness in light has to do with the amplitude of a vibration. And the amplitude of the vibration should be getting bigger when the light is brighter, and that should imply more energy. This was not the case, and it was a stunning revelation because it was backwards to what everyone thought. What he noticed then was, he said, well, if it's not how bright it is, let me try something else. Let me try wavelengths. So we all recall, blue light has a short wavelength, say around 400 nanometers, where red light has a longer wavelength, say around 700 nanometers. And all the colors in between are between those two numbers, generally speaking. What he found was that if he were to take a piece of metal and shine red light on it, nothing happened. There was no ejection of electrons. But the same metal with blue light shining on it, then he was able to see the ejection of electrons. In other words, the blue light seemed to have more energy than the red light. Weird. Even if he used the same brightness for the two lights, red and blue, it didn't matter. Brightness didn't matter. What seemed to matter was wavelength. So the wavelength is what determines the energy of a photon. It is wavelength, not amplitude, that determines how much energy a photon has. And of course, this means then that the old picture that we've drawn, we kind of knew this before, we drew radio waves and microwaves and all the way up the spectrum to the very high frequency, short wavelength, cosmic rays. And we said that the energy of those rays increases as wavelength gets shorter. So the wavelength gets shorter, the energy increases. And this is, of course, what Einstein had determined back then. We know this now because we live today. And we just take that for granted. But no one knew this at this point. Einstein figured it out. Okay, so now we have a very interesting situation. The photoelectric effect depends entirely on the wavelength of light, not on the amplitude or brightness of the light. Okay, so how does this all fit together? Let's just summarize, as it does seem a little bit complicated, and it's not really. It's just because it's all new to you, and there's lots of different things going on. So basically, the photoelectric effect can be summarized by the statement that when energy from a photon of light strikes a metal plate, that energy must do two things. It must liberate the electron, or free it from its bonds, which is what the amount of energy that the work function represents, and whatever is left over, if any, will be the kinetic energy. So what that means is if the energy of the photon is less than the work function energy, then nothing happens. It's not enough to break the electron free. Right? If the energy of the photon is equal to the work function, then you get a free electron with no kinetic energy, which again is sort of the in-between situation, and that electron would just be reattached. It's like, I just got out of jail, but I don't have enough energy left to run away. I used all my energy to break through the bars with my little nail file, and by the time I got done, I broke the bars and I collapsed on the doorway, and the jailer comes and just basically puts me back in, and I'm back in jail again. So no energy left to get away. You have to have a getaway. And then, of course, if the energy of the photon is greater than the work function, then you will have a free electron liberated from his atomic prison, and also he will have some kinetic energy to get away. So that's the summary of it. And of course, the other very important factor, that the energy of a photon depends on wavelength. Depends on wavelength, right? Or frequency, because remember that frequency is really just related to wavelength by the universal wave equation. And for light, the speed is set a constant c. So basically what this means is you could also discuss the frequency. As the frequency gets bigger, energy gets bigger, or as the wavelength gets smaller, energy gets smaller. Those two things. But typically we talk about wavelength more often than frequency. So those are the two key things to get from the photoelectric effect. Let's see how we could apply it in a mathematical situation. We'll do a little problem here. Let's see. Let's find... So there's a material, like a metal, has a work function of 2.3 electron volts. Now, of course, we have to use this tiny new unit. So let me just explain how that works. An electron volt is a special way of describing energy. It's another unit that we're going to start using. 1 electron volt. Now remember that voltage is equal to energy per unit of charge. For an electron, the voltage would be the energy, and the unit of charge is the fundamental elemental charge E. And so you can see that the energy then is E times V, and that's where it comes from. The charge of an electron times the voltage of an electron is an energy unit. So this does produce a unit of energy. I'll just erase that. So 1 electron volt has a conversion factor of being 1.6 times 10 to the negative 19 joules. So you'll want that number handy, because we tend to use the electron volt for tiny things like electrons, so we don't have to use times 10 to the negative, big numbers all the time in crazy scientific notation. A nice 2.3 instead of 0.0000000000034 joules or whatever. So that's just a simple conversion. The electron volt. When you see that, think energy. It's a unit of energy. Okay, so let's go back to our question. A material has a work function of 2.3 electron volts. What that means is it takes 2.3 electron volts of energy to knock one of its electrons free. If we shine light on it with a wavelength of 632 nanometers, which is about the reddish color of a typical helium neon laser beam. Right, that red light you get from a laser pointer is basically about that. If we do that, what will happen? Will there be any photoelectric effect? Well, the first thing we have to do is we have to figure out how much energy is represented by these photons of light in this laser. That would be the first deal. So the energy of a photon, remember Mr. Max Planck said that the energy of a photon is hc over lambda, right? So even Max Planck was aware of the fact that energy depended on wavelength, not so much on amplitude and vibration. And remember also that all of these scientists were working not all in the same room altogether. They were working very much individually. And they read each other's papers, and they took leads from each other, but they were, they weren't all working as a team at this point towards one common goal. They were kind of just looking at all the different pieces of the puzzle. So we have this from Max Planck. So we can figure out how much energy there is in that photon. It would be hc over lambda. Now, to figure that out, we would need to take 6.26, Planck's constant, 6.626, sorry, times 10 to the negative 34, very small number, multiplied by the speed of light, 3 times 10 to the 8. And then over here, we have to make sure we change the nanometers into meters, so that's 6.32 times 10 to the negative 7. Oops, you're not going to be able to see that. 7. Better fix that up in case some of you fell asleep and then you wake up a minute later and say, what? And then negative 7, there we go, meters. And when you do that math, it works out to about 3.143 times 10 to the negative 19 joules of energy. And then if we do the conversion to electron volts that I showed you before, basically 1 electron volt is 1.6 times 10 to the negative 19 joules. So if we divide that out we get an answer of about 2.3 electron volts. Oh, sorry, my mistake, not 2.3. I'm looking at the question. That's not correct. It comes out to about 1.96 electron volts. There's the energy in a single photon of helium neon laser light with a wavelength of 632 nanometers. But the work function of the metal that we are shining it on is 2.3 electron volts. So this is not strong enough to liberate any electrons. Nothing would happen. You basically just compare this to the work function. If it's lower than the work function, nothing happens. If it equals the work function, an electron can be liberated but without any kinetic energy. And then if it's greater than the work function, the electron can be liberated with kinetic energy and be able to escape. So in this case, nothing would happen. So the next question would be, well, what wavelength would we need? What wavelength, what lambda, would produce a photoelectric effect? Photoelectric effect. Well, let me just work it backwards. If the work function is 2.3 electron volts, we could convert that into joules using our conversion factor. It's about 3.68 times 10 to the negative 19 joules. So if this is how much energy it would take to knock an electron off, we could work backwards and say, okay, energy equals hc over lambda, right? And then we could plug in our numbers. So we would say energy, the energy that we need is 3.68 times 10 to the negative 19. Planck's constant, h, again, 6.626 times 10 to the negative 34. 3 times 10 to the 8. And we could figure out what wavelength would be required. And when you do this, you get a wavelength of about 510 nanometers, or 5.1 times 10 to the negative 7 meters. So you can see that that would not, that would be the smallest, or sorry, the largest possible wavelength that you would need, because as you get smaller, you get more energy. Anything smaller than 510 would eject an electron from this particular metal material. Now, let's go one step further then and do a part C. How fast, or let's just say how much kinetic energy? Well, no, you know what, let's go speed. What the heck? Because you'll probably get questions where you have to do speed. So let's go how fast. Well, a better way to put that, I keep changing my mind here. That's why you have to white out. A better way to put that would be, what velocity or what speed would an electron have if a wavelength of 400 nanometers was used? Well, now we just have to do all the math again and go through the process. So let's start with the E photoelectric effect equation. The energy of the photon of light has to liberate the electron by having the work energy, the work function energy, and anything left over will be kinetic. So what we see here happening is this would be hc over lambda, the energy of the photon. The work function is 2.3 electron volts. And we have kinetic energy, 1/2 mv squared. So there's our velocity. Don't confuse the volts with velocity. All right. So now we have to make a little decision. We have to have our units all in the same boat here. So we have electron volts of energy, but 1/2 mv squared kinetic energy is joules. So what we have here is joules, and over here EVs. We have to convert. There are two ways we can convert. I just realized I can't go any further down the page here, so I'm going to have to start a brand new page. Okay, let me just start a new page. We'll say no to that and hope it keeps going. It should be recording everything as we do it. So let's start again and say work function plus EK, right, HC over lambda, 2.3 electron volts, 1/2 mv squared. But the units, this is in joules, this is in EV. So either you do all EV and convert at the end, or you do all joules. It's up to you. It's possible to rewrite Planck's constant in terms of electron volts instead of joules. So what you could do then is you could write Planck's constant H. If you convert it to electron volts using the conversion factor, you get this, 4.4 times 10 to the negative 15 EV. You should write this down right beside where you wrote 6.626 times 10 to the negative 34, right? And it's actually EV seconds, and this one I think was joule seconds. So this is the version of Planck's constant. You have two of them. One to use when you're talking about joules, and one to use when you're talking about EVs, or electron volts. If you want to use Planck's constant in electron volts here, the answer you will get will be in electron volts, which means it can then be added with this one as the same unit. And then you would have to change it to joules to compare it to that. Or you could just start off here with joules to begin with and change this to joules so everything's in joules. So I think it kind of looks messy there, but you get the idea. You've either got to work all with joules or all with electron volts. So let's do joules, because I think that's probably the one that you're most familiar with. All right, so let's change joules. So we're going to use this version of Planck's constant, and we want it, the HC over lambda, then, to be 6.26 times 10 to the negative 34 times C, which is 3 times 10 to the 8. And then we want to divide that by lambda, which in this case was 400. So 4 times 10 to the negative 7. Watch that 7 is disappearing again there. And that's the HC over lambda. Then we have to change the 2.3 EVs back into joules. And remember, 1 EV is 1 so we basically multiply by the conversion factor 1.6 times 10 to the negative 19, because each one of those is that many joules. And then we have the 1/2 mv squared. So when you do all this math, now everything's in joules, you remember the mass of an electron, right? You remember the mass of an electron, so you should be able to do all this math and figure this all out. I'm running out of time. The bell's going to ring any second, so I'm going to pause, do the math quickly, and come back and give you the final answer. All right, so this came out to about 5 times 10 to the negative 19. And you notice how I forgot the 6 here. 6.626. That happens a lot because it's too many 6s. It gets that to be that. And the 2.3 times 2.3 times 1.6 times 10 to the negative 19 comes out to about 3.68 times 10 to the negative 19 plus 1/2 mv squared. And then, of course, you take this, you're going to have to subtract this from the other side. So 5 minus 3.68 Gives us with 1.32 times 10 to the negative 19 joules of energy equals 1/2 mv squared. We have to look up the mass of the electron again, which is 9.11 times 10 to the negative 31. So just look that number up, and then basically take your 1.2 multiplied by 2, divide by 9.11 times 10 to the negative 31, and you get a V. Don't forget to square root it, and you get your V that comes out of that. Now, I just got a very large V, so it looks like perhaps I have to go back and change some of my numbers. Unfortunately, time is running out for me here. I'm just going to double check. See, this number looks good. 2.3.
Thank you.
1.11 times 10 to the negative 31. And then square root, that's a better number. So it's just a math problem. Let's just quickly ignore that. Look at that. 3.8323-ish meters per second. Very fast, but at least within the realm of possible. Last one I got was bigger than the speed of light. So that's basically how you could use that equation. And I'm going to let you try a couple on your own, and if you have difficulty, well, we can work through them one at a time.